Ethylene feedstock to a polymerization reactor needs to have impurities less than about 40 ppm in order to prevent poisoning of the polymerization catalysts. Many MOF developments in the past have concentrated on the selective capture of ethylene C2H2 from ethylene to provide feedstocks of the required purity. In a recent development published in Nature Communications that is just available online, a new development has been reported in which a MOF, that is anion embedded and termed ZNU6, this MOF is capable of removing not just C2H2 but also any CO2 in the feed mixtures. And this MOF is capable of producing polymer grade ethylene of the required purity. From the breakthrough experiments shown here, the productivity of ethylene can be calculated from the breakthrough experiments as being equal to the molar concentration Ct, which is the total pressure divided by RT, times the volumetric flow rate of the gas mixture at the inlet, divided by the mass of adsorbent, times an integral from T2 to T1, that is the T2 is the time at which ethylene breaks through, and T1 in this case is the time at which CO2 breaks through. So delta T is that time interval, and this integral is the volume fraction of ethylene in the exit feed mixture times dt. This integral can be determined by, say, Simpson's integration of the breakthrough data determined from experiments. The productivity thus calculated is 13.8 moles per kilogram, which is a new benchmark. In a more recent MOF development that is described in the paper by Howe and others, published online in Chemical Engineering Journal, it is shown that an ultramicroporous bismuth MOF functionalized with CHO group is also capable of one-step purification of ethylene to prepare feedstocks for polymerization purposes. The important difference between bismuth MOF-CHO and ZNU6 described in the foregoing slide is that bismuth MOF-CHO adsorbs CO2 more strongly than C2H2, and for a 1,990 mixture of C2H2, CO2, C2H4, the sequence of breakthroughs is C2H4, C2H2, and CO2. The corresponding breakthroughs for a 1,199 mixture of C2H2, CO2 and C2H4 is C2H4, C2H2 and CO2. During the time interval indicated here, ethylene of the desired purity containing less than 40 ppm impurities can be recovered from the feed mixture. This development of Bi-MOF-CHO is on the basis of grand canonical Monte Carlo simulations of adsorption isotherms and transient breakthrough simulations using the unary adsorption equilibrium data. There are certain advantages of using MOFs that are more selective to CO2 than to C2H2, because such MOFs, for example, Bi-MOF-CHO, can be used to produce high purity C2H2 from mixtures with CO2.